everyone, this is Miss Moriarty, and I'm here to discuss with us our topics 1.8 to 1.11. I know that we did most of these topics in class today, but I just wanted to re-record just in case you may have missed it in class. So remember from our class discussion, we first mentioned primary productivity. This is going to be our rate at which solar energy is converted into organic compounds, specifically glucose, via photosynthesis over a unit of time. The two main vocab words we need to know here is gross primary productivity, which is total rate of photosynthesis in a given area. Net primary productivity is now the rate of energy storage by those photosynthesizers in that given area after we've now accounted for the energy lost to respiration. Here is a diagram depicting what I was just mentioning here. So we have our incoming solar energy strikes Earth. Producers actually only capture about 1% of that incoming solar energy, while 99% of that is actually reflected or passed through producers without being absorbed. 60% of the GPP is actually lost to that plant's then respiration, while 40% of it is moved on, and that's going to be the net primary productivity. So that supports its growth and reproduction of those producers, and when consumers consume those plants, that's the energy that's passed on. We can see a pattern specifically when we look at the net primary productivity of biomes. Productivity tends to be highest where we see high temperatures, as well as lots of precipitation and available solar energy. So, in terms of continental ecosystems, swamps, marshes, and tropical rainforests tend to have very high net primary productivity versus, say, the tundra or deserts, which have very either low temperatures, low precipitation. In marine ecosystems, we tend to see coral reefs are very high in terms of their primary productivity versus the open ocean, which is quite low. Here was the practice multiple choice we discussed in class. Here it gives us our GPP of a wetland versus its respiration. You had to find the net primary productivity, which was 1.5. Moving on to topic 1.9, this was all about trophic levels. So in this unit, we've focused so far a lot on how matter is cycled through ecosystems. Here we're going to talk about now energy flow through those ecosystems. Both matter and energy are always conserved, which means that they are neither created or destroyed. They simply change forms. And when we look at energy flow in an ecosystem, we measure it by looking at trophic levels. Energy tends to flow from the sun to then producers, which are our lowest trophic levels, and then move upward to the higher trophic levels. Typically, we depict that flow of energy in the form of a pyramid. Our producers are the largest set of organisms in terms of number. They also obtain the most energy, so we place them at the bottom versus our primary consumers, secondary and tertiary. You can see as you move up in trophic level, energy then decreases. That energy flow and decrease typically follows a rule, and that rule is called the 10% rule. This is simply just an approximation in how that transfer of energy moves from one trophic level to the next. That loss of energy that occurs is explained through two laws of thermodynamics that we need to know. So here's just another diagram kind of depicting what I was mentioning before. Here's another trophic pyramid. This kind of shows us the amount of energy present at each trophic level, but now it's measured in joules. Now, while this pyramid assumes about 10% ecological efficiency, the actual efficiencies can range from 5 to 20%. But for most ecosystems, graphing the numbers of individuals or biomass actually produces a similar pyramid as our energy pyramid. And so here's just a quick practice math question. In a cedar bog lake in Minnesota, scientists measure the productivity of our producers, consumers, and secondary consumers using the table values below. You have to calculate the percent energy transferred from producer to primary consumer, and so on. So in order to find the energy transferred from producer to primary consumer, we take then the productivity found at the primary consumer level and divide that by the producer level. We multiply that by 100, which gets us at about 13.3% energy transferred. Versus looking at the primary to secondary consumer level, we can see about 20.9% energy is transferred. And remember, that 10% rule is simply just an approximation. Real ecological efficiency can range between 5 to even 20%. Now, remember, we have that range and we have only a small amount be transferred because of our laws of thermodynamics. Now, the first law we need to know is that energy is neither created or destroyed, right? You can't get something from nothing. The second law is when energy is transformed, right, changed into different forms, that quantity of energy remains the same, because recall, we can't destroy it, but its ability to do work diminishes. And so oftentimes the second law of thermodynamics tells us that as we increase in trophic levels, we're also going to increase in entropy or disorder. And so here's another math practice question, calculating the overall efficiency of two different systems in a power plant, looking at coal versus natural gas to electricity. Our coal to electricity is really only about 6% efficient versus our natural gas to electricity is about 11% efficient. The last topic of Unit 1 is 1.11, and this is looking at food chains and food webs. We know that a food web is a model of many different interlocking food chains that are going to depict our flow of energy and nutrients in our given ecosystem. Positive and negative feedback loops do play a role in food webs. So when one species is removed or added to a specific food web, we can see that the rest of the food web may be affected. Specifically about food chains, we can see a simple food chain just links our producers and consumers in a linear type fashion. It shows us how energy and matter might flow through levels of an ecosystem. Versus our food web, which gives us a much more realistic representation of our trophic levels. And not only do food webs depict to us our producers and consumers, but we must also include things such as scavengers, detritivores, and decomposers, because those species are often also found in trophic levels and they help to cycle nutrients into the ecosystem. Also, recall that our food webs and food chains, when depicted, typically have arrows, and it's those arrows that indicate the direction of energy movement. All right, everyone, that is the end of our Unit 1. Make sure at the end of this video, please just mark it as done.